All right. So today, Nathan and I are going to speak about Pantera. It's a tool that we created to meet the challenges of visualizing very large data sets. Specifically, how we use Spark to create an interactive high-density data visualization framework. Hopefully everyone this morning saw us at the keynote where we did a demonstration of the software. So to that end, this afternoon, we only got 15 minutes, so I'm going to be relatively quick. I'm going to show a bunch of visual examples, some geographic and some non-geographic examples. And then I'll hand it over to Nathan, and Nathan's going to talk about some of the technical challenges we faced in creating the software and how we approach them in Spark. So first, I'd like to take a look at what might be considered a traditional geospatial visualization. It heavily relies on aggregation, regional aggregation. That is, generating summary values, one or two summary values, and displaying them like this over top of a map. But the problem with this is that the regions that we're aggregating to can be totally arbitrary. Maybe they're political or are defined by physical geography. But the problem is that within these regions, the regions don't necessarily fit our data. And a lot of the patterns and nuance of the data that actually lives inside these regions is totally lost by doing it this way. Unless we know a priori how to set our region boundaries based on the data that we have, we're probably going to be losing a lot of significant information. However, this is sufficient for some analytical questions. But when we have more resolution in our data, we need ways to look it up. So how about something like this? This works. I mean, here's 20,000 points. I don't know if you can tell that's 20,000 points, but it is. And while we see some notion of distribution, a visualization like this suffers badly from overplotting. You can't see density, you just see a lot of dots. Also, the scale is limited. If I told you I'd just throw up 100,000 points on here, would we get much more out of it? Would we be able to tell? Probably not. So the first slide showed about 100 unique values, and the second one, arguably 20,000. We can see a lot more. We can see hundreds of thousands, because our eyes are very good at looking at visual data and picking up patterns and anomalies in high-density graphs, such as this. So we can break up these aggregates and show right down to the individual resolution of the pixel on our display. And we can explore the details underneath, and also show the density of the data. So this, for example, I showed some taxi data this morning. This is actually average tip percentage by pickup location for the taxi cabs. And at this level of detail, I can see a relatively noticeable anomaly right there. And this is a block, one block south of the Empire State Building, one single city block that has an abnormally low tip percentage compared to all its neighboring regions. Similarly, earlier we saw the side of the street that you stand on really makes a difference when you're trying to catch a cab. These details can reveal important patterns or errors or incorrect assumptions that you've made about your data. It can reveal new hypotheses and insights, or really show some nuance to the data that you might have otherwise missed with some of the previous methods. But there's often more to our data than just breaking up these things into individual pixels and showing static views of the data can show. Different patterns can exist over vastly different scales. For example, here we've plotted 1.6 billion Instagram posts over the summer of 2014. We see a global picture of who's using the service and where. I think Automatic said the same thing. There's no map behind this. This is strictly data defining our geography. So we can see a lot of interesting patterns. But what if I zoom into the eastern seaboard of the US? I see slightly different information at this scale. I'm able to use my pixels to map to a finer degree of density. So I see population centers, and I see suburbs radiating out of downtown cores very clearly. And interestingly, I can also see road networks, which I think is very interesting since this is Instagram, a lot of people taking pictures on roads. But I also can see a significant error in my data that I've blown up right here. There's a significant amount of the data here that's likely at the right latitude, but definitely at the wrong longitude. So it's being projected way out into the ocean in this straight line. So what's really interesting about this error is that it's only occurring at this very specific latitude. One latitude is causing our collectors, or whatever devices these are, to have very, very incorrect longitude values. I zoom in once again, and at this scale, I can see downtown Manhattan, and I can see something that looks a little bit more like the taxi data. I can see the physical geography, like streets and bridges and parks. For example, here is the Brooklyn Bridge, clearly a popular spot to take photos. But I can also see another type of error at this level. It may not be clear in the projecting. Actually, it's not bad. But I've highlighted with arrows. There's some percentage of the GPS readings that we're getting here that are reporting rounded or truncated coordinates, either on both longitude and latitude. But what's really interesting is sometimes it's only on one of the two. So what we're actually getting is we're getting this grid-like projection over top of the city. So by looking at the data at this resolution, we can actually see that we are getting these incorrect values. So if you're trying to use it down to like block level analysis, I think someone brought up earlier, like being on the wrong street corner and stuff like that, this is significant because there is a fair amount of data that's incorrect like this. So being able to interactively explore the patterns at all different scales provides a lot more information that you can get out of a single static view of your data. So the on-demand generation of this provides an interesting tech challenges. Traditional visualization might use 10, 100, or even 1,000 summary values, but we require hundreds of thousands. And once you start zooming and panning around as we generate more views, that can climb into the billions of generated points. So to talk about how we use Spark to do this, I'm going to introduce Nathan to the stage.
Hey there. Before we get too much into it, I want to explain a little bit of what tiles are and how they work. The basic approach we're using is adapted from the mapping domain. It's the same method Google Maps and the like uses to manage their data, only applied more generally. One creates a quad tree for mapping small bitmaps. The top level would be a single small bitmap that shows the whole world. The next level would be 4 that each show a quarter of the world, and so on, each level showing 4 times as many as the one above it. And the reason we use this approach are the same as those driving mapping programs. First of all, it is efficient. It allows you to get exactly the data you want, no more, no less. And especially when you're panning around your data, it allows you to reuse what you've already gotten. Second of all, it eliminates a lot of zoom artifacts. When just about any other scheme you could possibly use results in pixels here and there flickering in and out or vibrating left and right that looks terrible and is very confusing to the user. And both of these, the ability to pan and zoom freely and smoothly, allow you to focus in on exactly the portion of the data that's relevant to your problem, without knowing ahead of time what that would be. On a typical display, such as the one we're using here, it's covered by about 10 tiles of 256 squared pixels each. This works out to about 2/3 of a million pixels, which we're trying to calculate on the fly at interactive speeds as you're panning around. And so I want to discuss a little bit how we're doing this efficiently. The naive approach from a MapReduce Spark perspective is you start with your raw data. You annotate each record with the tile and bin or pixel in which it falls. You aggregate all the data within a given pixel together, and then you aggregate all the pixels within a given tile together, and you're left with the tile of the data you need of that particular portion of the screen. That's it. It's fairly simple. It's also fairly slow. This requires 2 shuffles. And though there are different performance curves in different situations, generally the first shuffle is very slow at high levels, and the second can be almost as slow at low levels. But in either case, it's way too slow for interactive speeds. So, how do we get this faster? We alter it a little bit. This was our second approach. We again started with the raw data and annotated it as before. But this time, within a given partition, we aggregate all the data for a given pixel, and then we collect it by tile. And this leaves us with a single shuffle. There are some drawbacks. We're using more memory on the map side, though we do have less object creation. And the shuffle side also has more to do. It's, in addition to just aggregating the bins into a tile, it has multiple values per bin it still has to aggregate. But in the middle, we're left with a single, relatively small shuffle. And overall, it's much faster. And this is a general lesson we've learned, that one can often speed up a lot of algorithms by doing what work one can within a partition before starting to mix partitions. But it's still not optimal. We still have one shuffle, and shuffles are, by their nature, costly and long. If we could eliminate this, we could probably get even faster. Can we still? Well, obviously, if the answer was no, I wouldn't still be talking. We do this using accumulators. Here we just run over our data once, map it into the form we need, and put the results into a tile accumulator. Now these are huge accumulators. With simple numeric data, each one's about half a meg. And with matrix or array data, this can get arbitrarily large. But it's still small enough that we can fit the 10 to 25, depending on the display, tiles we need for any given visualization. Here's some timing tests with it. This is the same query run across different Databricks clusters. And we can see that consistently across different cluster sizes, the accumulator approach is about 4 seconds faster. And if we make different sized requests, the cost time is linear, but it's a much higher slope in the non-accumulator method. Now, Rob and I both mentioned this is a standard technique of mapping programs. Actually, you didn't. I guess only I did. But we both said this is not limited to mapping spaces or mapping data. We've applied this technique to all sorts of data sets, from IP network data to social media, from graph display to financial data, sometimes numeric, sometimes otherwise. And I'm going to hand this back to Rob, who's going to show us some interesting insights we found just last week when looking at some financial data.
Thanks, Nathan. So I'm going to focus on Bitcoin. I think I mentioned that this morning during the keynote. And here's a quick graph of showing transaction volume and average Bitcoin price from the Mt. Gox exchange over about a 2.5-year period. So what I'd like to do is take this type of data and look at it over a 4-year period. And I think there's about 37 million transactions over this time. So if we plot it like this, in our tool, what we're doing is we're plotting time on the x-axis and the logarithm of the transaction value on the y-axis. And the intensity of each pixel maps to the number of transactions at that time at that value. So what we see is clearly an increase in volume of transactions, an increase of distribution of transaction values over the first 4 years of Bitcoin's life. We can see a constant 50 Bitcoin line. 50 Bitcoins is the mining reward, and that existed all the way up until near the end of 2012 when it halved to 25 Bitcoins. But we can see some really interesting patterns at this scale as well. This group down here is extremely low value of transactions, 10 to the negative 8 Bitcoins, or between 1 and 100 Satoshi, which is like 1/10,000th of a penny. These start together, they slow together, they stop, they restart perfectly coordinated in time. And what we're seeing is actually one of the first cases of a denial of service attack on the Bitcoin network. It involved flooding the blockchain with high numbers of very, very low value transactions. And a revision was made to the Bitcoin code shortly after this to penalize and reject these types of transactions, and the attack stopped. I can also see an interesting pattern here, where it looks like I've got sort of a trace falling in value over time. And what I understand from what I read is this may be a pattern called peeling. Peeling is a pattern where a large quantity of Bitcoin is split into many, many smaller amounts, one transaction at a time. So a small amount is peeled off each time. And it can be used to distribute coins among a large group of people, for example, a mining pool. But it can also be a way to hide the movement of funds that may have come from an illicit source. And the last pattern I'd like to look at in this data is buried here in the middle of this really high value intensity area near the end of the data set. And when I zoom in to a much closer scale, what I see is a pattern that's similar to the peeling patterns we saw at the very beginning of the large scale, but at very, very different scale here. What we see is short value runs. They all start between about 15 and 20 Bitcoin, and they drop by about 2 or 4 Bitcoin at a time. They span for about a day at a time, and they're strictly sequential in time, one after another. And if we zoom in using the tool right down to the individual transaction level, each one of those white pixels there is one transaction, we see the trails are made of very, very closely spaced transactions. There's thousands of them per minute, and they're about 2,500 Satoshi apart, which happens to be the minimum allowed transaction value in the Bitcoin network at the time. If they're peeling tiny amounts at a time. It's very interesting. So Pantera's ability to allow this multi-scale exploration to dive right down from the very top 4 years, right down to the individual transactions in minutes, allows us to discover and explore these patterns as we see them, and to form new hypotheses based on what we see. So where do we go from here? All of our examples so far have looked strictly at numeric data, but we've created a general approach to multi-scale data visualization. Because of the functional nature of Spark and Scala, we can apply this to really any types of data, matrices or even textual data. So example on the left, we've applied it to social media and hashtags and common terms. And we've also applied it to biomedical imaging. We're also excited to be working on streaming support so that we can have much more lively data. And we're also working on new interaction capabilities to provide a visual metaphor to Spark's already really interesting exploratory workflow. So that's all the time that we have for today, and I probably don't have time for questions, but Nathan and I are around all day, so just grab us or hit us up on Twitter or shoot us an email if you'd like to discuss further. We're also at www.pantera.io for more information. Thanks very much.
So one question, if we can answer one question until Jan gets set up.
Yeah, absolutely. I'd
one
love to.
question, guys. Sorry.
So you mentioned 20,000 points and 100,000 data points. What about size of the data you bring to the front end?
Right. So So like the Instagram example is 1.6 billion. The Bitcoin was 37 million. The amount of data that we bring is basically proportional to the number of pixels on your display. But as you zoom in, if you're looking at the entire world, I maybe am looking at 1 million pixels for the whole world. Then I zoom down to a city block. I'm looking at 1 million pixels for a city block level. So it's like sort of multi-scale in that sense.
How many megabytes?
Well, I think what you're asking is more what sort of input data can we handle?
Yeah. How much data can you bring to the front end with reasonable time frame?
We're bringing a constant amount at a time to the front end, like he was saying. It's if your front end is 1 million pixels, we're always bringing 1 million pixels to the front end. What data is on the back end being processed by Spark, that's dependent on your cluster size. That's not so much a factor of what we're doing.
Right.
Okay,
It's a web application. It's JavaScript front end in a browser. It's very snappy. I mean, it's based on the same principles as web apps. So, yeah.
Thank you, guys.
Yeah,
Very
thanks.
interesting. Thanks.